Good evening, ladies and gentlemen. It is a great pleasure for me to welcome you to the online public lecture organized by the Szczecin branch of the Polish Physical Society, together with the collaborating partners of the Alte Cosmofan 21 conference, Alternative Gravities and Fundamental Cosmology 21 conference, the University of Szczecin, the National Center for Nuclear Research in Warsaw, the Maritime Academy in Szczecin, the Copernicus Center for Interdisciplinary Studies, the Jerzy Stelmach Eureka Foundation, and the MDPI Switzerland, an editor of the journal Universe. I warmly welcome all the participants of the conference, as well as the public who joined us for this intended to the public lecture. I welcome politicians, representatives of the local authorities, businessmen, journalists, professionals, the university faculties, and in particular, the young school pupils, as well as high school and university students. Welcome, of course, members of the Polish Physical Society and fans of physics, cosmology, astrophysics, and related topics. By default in Zoom, all the participants' microphones and cameras are made inactive. Please try to use chat option for asking questions unless you really feel like having them online. I would like to say that today we have a public lecture by a distinguished professor, Luciano Rezzolla, who is the director of the Institute of Theoretical Physics at the University of Frankfurt, Germany, and the Andrews Professor of Astronomy at Trinity College, Dublin. Couple of words about the professor's career. Professor Rezzolla, born in Milan, in fact did his PhD at the International School for Advanced Studies, in short in Italian SISSA, in Trieste, Italy in 1997. He then visited as a postdoc at the University of Illinois, Urbana-Champaign, after which, in 2000, he came back to Trieste, working as an assistant professor, sharing his work with Max Planck Institute for Gravitational Physics, which is also known as the Albert Einstein Institute in Potsdam, Germany. In 2013, Professor Rezzolla started work at the Institute of Theoretical Physics, Frankfurt University, where he was appointed a director of the institute in 2017. He was nominated the Andrews Professor of Astronomy at Trinity College, Dublin in 2019. Professor's main research interest fields are theoretical physics and astrophysics, general relativity, high energy phenomena from compact objects such as black holes and neutron stars. He worked on gamma ray bursts, P-mode oscillations around black holes, blitzars, and gravastars, among others. Since 2015, he is involved into the work on the data from Event Horizon Telescope. Professor Rezzolla published more than 200 research papers, which were cited more than 13,000 times, and 67 of his papers were cited more than 67 times, which means that Hirsch index for his publications reaches H equals 67. Professor Rezzolla also co-authored the book on relativistic astrophysics, relativistic hydrodynamics. It is difficult to count numerous achievements of Professor Rezzolla, but I would like to mention the two. The Karl Schwarzschild Prize in 2017 and an Outstanding Personality 2019 from Frankfurt am Main City Council. Finally, it is worth mentioning that Professor Rezzolla also has some interesting private activities. He sails a boat Era and rides a bike Viola. Luciano, Professor Rezzolla, the screen is now yours. Please provide us with the recent achievements related to the black holes.
Very good. Thank you very much, Mariusz. This was a very extended presentation of myself. Almost embarrassing. Let me thank you for the kind invitation to deliver this public talk. And I hope you can all see my screen. So as the title goes, I will be telling you about the first image of a black hole. And I'll try to strike a level which is sufficiently detailed and rigorous for people who are physicists professionally to appreciate the content of my presentation, but at the same time, sufficiently simple that anybody also who is not an expert in astrophysics or in general relativity can understand what has been achieved. So here is what I will tell you about. I will try and explain how you take a picture of a black hole, and I will do this by splitting the observations from the theory. And these are really distinct, and within the EHD, they really have worked in two separate steps. I will then tell you about how you can compare observations and theory and obtain something that you convince is correct. And then, because I'm a theorist and we tend to never stop thinking, I will tell you a little bit about possible alternatives to Einstein and even to black holes. Okay, so before we start, let me just explain that we have a problem. And the problem is the following. Black holes are, by definition, the most compact objects in nature. You cannot confine mass or energy in a smaller volume than in a black hole. In fact, if you take a star, you can compress it, and only when you compress it enough, you will produce a black hole. Black holes, on the other hand, are astrophysical objects, the ones at least we know of, and luckily, in that respect, they are all astrophysical. That means they are at astronomical, huge distances. Now, if you take something which is very small and you put it very far away, obviously, it's going to look very, very small on your sky. So if you want to take a photo of a black hole, the first thing you need is a black hole with a resolvable size on the sky, or you simply will not see it. That's why we normally don't see black holes with our telescope in the galaxy. So the only solution to this problem is that you need a very massive black hole, because the size of a black hole grows linearly with its mass. But at the same time, it has to be sufficiently close to us, because it doesn't matter how big it is. If it is too far away, you simply will not see it. So people in the EHD start thinking about what are the possible candidates. And one candidate that immediately came to mind is M87. M87 is an elliptical galaxy. It's at the center of the Virgo cluster. And we know that there is something like a dark mass, which we cannot see, which is of the order of between 3 or 6 billion solar masses. This is a typical image of M87 in the optical. And you can see that there is a little filament over here. In fact, at the beginning, people thought this was a comet because of this filament. Now we know it is not the tail of a comet is actually an ultra-relativistic jet of plasma. Now, if you imagine of wearing radio glasses, that's what M87 would look like. So it is much bigger in the radio. You can see emission from a huge scale, 250,000 almost light years. And of course, you know, if there is a black hole, it's right there at the very center. So what you would like to do is to have a telescope that allows you to zoom in into this image and look at things at this scale. And this is what you can do with a technique which is called VLBI. So with a VLBI technique, and which I will explain, you can zoom in. And then once you zoom in, you can see that there is a clear jet of plasma on scales which are enormous. And you can further zoom in the inner part of the jet and you obtain something like this. And you can further zoom in the inner part and you obtain something like this. That is the kind of resolution that people had before EHD observations. But what we wanted to do with EHD is actually obtain a resolution of the size that I've shown you in this image. So we wanted to have something which is at least 1 order of magnitude, or actually more than 1 order of magnitude smaller, and look at what happens very close to the center, to the center of the galaxy, and in particular to the place where the jets seem to be originating from. When we started looking at this, we had no idea how big this object was. We just knew what was our resolution. So nowadays, you don't do any serious science if you don't have an Hollywood-like type of movie. And of course, we do very serious science. So we have a very Hollywood-like movie. So let me show you what we've done through this Hollywood movie. We look at the Virgo cluster, and essentially we look at the M87, which is just a little dot in this picture. And then we use this technique. We first, you can imagine of diving into M87. You can still see it as a galaxy in the optical, but then you will need at one point to switch on the radio observations once you get closer to this jet. And that's, you know, now you're looking at it in the radio, and you can further zoom in and zoom in and zoom in. And at the end, that's what you get. That's the image of, the first image of a black hole. And I will now explain how you actually do this. So the technique one has to use is called very long baseline interferometry, or VLBI in short. And there is a very simple equation that describes this technique, well, actually describes any astronomical observation, and is LADECT. The resolution, which is essentially the angular size on the sky, so you want a number to be as small as possible, is just given by the ratio between the wavelength at which you're making the observation and it's the size of the telescope you want to use. Okay, so because this number has to be small, you would, in principle, no, you would think naively, let's use the smallest wavelength, that is, I don't know, gamma rays. That doesn't work. The reason is that gamma rays, just like X-rays and so on, down to the infrared, are mostly absorbed. So, I mean, the light that is emitted near the black hole, that's producing these wavelengths, is almost all absorbed. So what you are left with is essentially waves that can be propagated without being absorbed. And you find out that the only waves that do that are actually radio waves. And so the smallest radio wave that you can use is 1.3 millimeter, which is 230 gigahertz. So we fixed the numerator, we need to fix the denominator here. Well, you know, radio telescope, this is a radio wavelength, so you need a radio telescope. You can build rather large radio telescope, 500 meters. There is one in China, FAST, which is 500 meters in diameter. So it's quite big, but that would not be enough. What you really want is the largest possible radio telescope. And this is where EHD enters into the game. The EHD created a virtual telescope, which has the size of the Earth at these wavelengths. And this is something that people had not done in the past. So how does this work? Well, you know, you just take a bunch of radio telescope, small radio telescope, 20, 30 meters in diameter, and you connect them through this technique. So for instance, you can connect a telescope in Arizona with a telescope in Hawaii, and then all of a sudden you have a virtual telescope, which is as large as the distance between Arizona and Hawaii, which is about 2,000 kilometers. So you have a 2,000 kilometer telescope. Now, the first time you hear this, you start thinking, wait a minute, this seems a bit funny. How do you actually do this? And why don't we do this for all wavelengths? So the catch is that in order for you to do this, you have to make sure that you're really observing exactly the same radio wave, the same wavefront. And that is why each of these telescopes has, together with very sophisticated high frequency receivers, also very accurate atomic clocks. In this way, you can record not only the electric field of the signal that is arriving, but also the time of arrival. And once you do this, then you really can have a single telescope and record things as if it was a single telescope, as if it was just different parts of the same telescope. Now, because we have many telescopes, we may as well use all of them. And there is an advantage in doing this, two advantages. The first one is that depending on the distance between telescopes, you have different resolutions. So it is like using images at different resolutions. And the second advantage is that, well, you know, the Earth rotates, which means that if you just use two telescopes, at one point, these two telescopes will no longer see the source, and they will, you know, the source will eclipse. And so if you take on other telescopes, then all of a sudden you have the ability to observe for many hours, actually a fraction of a day. Of course, it would be nice to have telescopes also here, so we would have a full coverage, but that's not the case. Anyway, we have lots of telescopes, and that's what we've done in 2017. So EHT doesn't own telescope. It just obtained time on telescope through competitions. And of course, we try to get the time all at the same moment. And then we send people around. So this was in 2017. You see the people in Mexico, in Chile, in the South Pole, Hawaii, Arizona, and Spain. And if you look at these images, you will see that there is something in common. All of the people that are there, and there is nothing on the South Pole, but all the people who are there are smiling. Now, if you ask yourself, why is that the case? You will find rather amusing to know the answer. Everybody is smiling for the very simple reason that there is sunshine. And that's because essentially these radio telescopes are supposed to get signal coming from 55 million light years away. So it's taken 55 million years to get to us. But then it's sufficient that there is a cloud just a few kilometers above the telescope, and that wavelength would be absorbed. That's because clouds, water vapor is the biggest enemy of radio waves. So everybody was happy because it was a perfect weather for doing radio observations. And as a matter of fact, we did other observations most recently in 2021. We never had as good weather as the first time. So in the 11th, so the 10th of April 2019, we published our results. The 11th, you can see that the image is on the first page of all the newspapers. It has been calculated that about 4 billion people have seen the image in the first 24 hours. So it's, you know, essentially a good fraction of humanity has seen the image in just 24 hours. And, you know, there are many different explanations of why the image was so popular. I think my explanation is that it was, you know, a perfect inspiration for social media. These are some of the interesting interpretations that social media produced of this image. And of course, you know, some of them are just, we didn't quite understand that this was the case. But so people use this to make jokes, and all of a sudden the image became super popular. To give you an idea of the size, this is really astronomical. This is the size of the solar system, that's Pluto. This is the position of Voyager. And as you can see, you know, Voyager, which is the most distant object, human object launched, is just at the edge of this dark region, which I explained is called the shadow. Now, how do you do the observation? I've explained that you need radio telescope, you need many radio telescope, but let me be a bit more precise. As I explained, you have different telescopes who have different baselines, we call them. And each of these baseline provides information in a Fourier space. And this Fourier space is a Fourier space where you decompose the intensity of the radiation into a Cartesian coordinate system, which is the system where the image is produced. So as you can see, there are baselines of different colors. And as time goes on, these lines track portions of this space, which is called a space of visibility, is this complex quantity over here. And on the basis of this information, you can produce an image. So if you want, more familiar with Fourier transforms and Fourier spaces in the frequency versus time domain, you have to imagine that this is the frequency domain and this is the time domain. It's just that here is a two-dimensional Fourier space out of which you build an image. So as time goes on, the space of visibility is filled more and more, and the quality of your image improves. This is an animation that shows that how at the beginning you have very little information. In fact, you have just the basic information, but then as time goes on and the Earth rotates and you can collect more and more data, you can populate more data here and you have a sharper image. So these are the 4 images that were produced over the 8 days during which we observed M87. This is the result of a huge amount of observational work and calibration of the data and conversion of the information in the visibility space over to an image. And this was done in a blindfolded way by 3 different groups, and each of which, actually 4 different groups, each of which produced some results which we then compared. These are the consensus images. These are the images everybody agrees on. And as you can see, they are referred to 4 different days, and they are different. They are not identical. But that's exactly what we would expect. We would expect an image that varies between days, but that overall, that is, whose timescale of variation is much, much longer. That's because we're looking at a supermassive object, and the typical timescales associated with this object are millions of years. So the fact that we see something like this is exactly what we expected. And at that point, this is when we enter into the scene. Essentially, our colleagues gave us these images and said, okay, now you tell us what is it that we're seeing and why it looks like that, and what we can tell about the properties of this donut. And what we've done is essentially can be summarized into 3 different steps. The first one is called GLMHD simulation in arbitrary spacetimes. GLMHD stands for General Relativistic Magnetohydrodynamics. Essentially is a way in which we study what happens to plasma when it is accreting onto a black hole. Imagine you take a bucket of plasma, you throw it onto a black hole. You want to understand what happens to this bucket of plasma. The second thing is, as this bucket of plasma falls onto the black hole and gets heated and shocked, will emit light. And this light has to reach an observer at large distances. And this is far less trivial than you may imagine. So we need to ray trace the light that is emitted from this accreting plasma, understand how much of it is absorbed and how much is scattered and re-emitted, and then take into account the fact that we have real radio telescope and not infinitely resolved images. In this way, with this step, you build tens of thousands of images, but we have just 4 images. And so the last part of this theoretical work is to do the comparison with observations. We were very lucky in that the European Union provided me and my colleague, Aino Falken and Michael Kramer, with very generous funding through a synergy grant, an ERC synergy grant. And with this in particular, my group in Frankfurt has built 3 different codes that do exactly these 3 different steps. They're called Bach, Boss, and Gina. And these are the real heroes of this story. These are all the students and postdocs that have worked very hard to produce these codes. So what are these codes doing? This is a bit technical, but not too technical. Essentially, we need to solve some equations of relativistic magnetodynamics. So we need to conserve energy and momentum rest mass, we need an equation of state, which is normally rather simple. And because the energy momentum tensor is the composition of the contribution coming from the fluid and the electromagnetic part, we also have to take into account additional conservation equations, essentially the Maxwell equations. And you have then to build numerical codes to solve these equations, and these have to be done in 2D and in 3D. And in addition, you need to solve the general relativistic radiative transfer equation. This is an equation that tells you how the intensity of a bundle of photons changes along the trajectory, geodesic trajectory of a photon. This expression is given by some emission and some absorption. And essentially, this is a Boltzmann equation for a gas of photons. Now, once you have done all of these and solved all of these equations, you obtain some result that looks like so. This is a typical accretion example of a plasma whose density I'm showing in yellow and red. And then there is this white-blue portion. This is the, it's not the density, this is the magnetization. So this is a measure of how intense the magnetic field is. And as you can see, the flow is far from being laminar, as you may imagine. Actually, it's very turbulent because there is an instability that drives accretion. And so there are times where there is a lot of matter falling in and matter is very compressed, and other times when there is far less. So there is a quasi-steady accretion. And so there is a quasi-steady emission of this relativistic plasma. Now, this is roughly the inclination at which we think we're looking at M87. And what I will do now is I will imagine what I would see if instead of having a visualization, I would have eyes sensitive to the radio emission. So this is a radio emitting ring of light, and looks very simple and very symmetric. That's just because we are in a very special inclination. If you start moving around this radiation field, you would soon realize it's far more complex. And I will explain why it is so complex and why it looks like that. And now, if you imagine that you're seeing this through a telescope, a radio telescope, that's what you would observe. You would observe something which is more luminous in the bottom, is flickering on timescales of tens of hours. And this is what we've seen. So, Marius, am I still connected? Because there's always the fear that I'm disconnected.
No, yes, you are connected. Yes, perfect.
Okay,
perfect.
Very good. Now, that movie explains what happens to plasma when it accretes onto a black hole. What happens to light? Well, in order to explain this, imagine that you have a black hole. And imagine that you have a very thin layer of plasma that is emitting light. That's what we call a thin disk. Thin disks do not exist on supermassive black holes. But for the sake of the argument, let's just imagine we want to visualize that. And we want to visualize this us as an observer with a given inclination. So what is it that we would see if we were standing here? Well, we would certainly see all the light coming right directly from the forward part of the disk. This is what we call the direct image. However, this is a curved space-time. So light that would otherwise go like this can also be bent. And so what you actually see is also light coming from behind a black hole. And to make things even more interesting, you can see light also coming from the lower sheet of this thin disk, and is essentially this part of the image. So this is an image that you probably all know because you watched it in the movie Interstellar. And this image is not wrong, but is not right either. I mean, there are a few details that are not right physically, but it's, I hope that by now you understand why it looks like that. You're seeing the first part of the disk, you're seeing the part that is behind the black hole, and you're seeing the lower part of the disk. You also see this very thin ring of light. We call it a photon ring. It's essentially a place where photons spend quite a lot of time, and so that is why it's in general brighter than anything else. Another thing you learn through this image is that it doesn't help if you have to hide, just don't go behind a black hole, because it doesn't help. you will be seen no matter what. So in reality, and this is what Interstellar got wrong, the disk is not thin, but is geometrically thick. I already explained this. And, you know, depending on the inclination at which you're looking at it, you will see it to be with a very complicated shape where you have two dark regions and something at the front. If it is perfectly face on, then it's uniform, but only in that very specific case. In any other case, there is always a portion of the disk which is coming towards us and hence is brighter. That explains why in the M87 image, there is one portion, the lower portion of the image, which is brighter. That's just because there is a Doppler boosting effect and there is matter in the disk coming towards us and therefore being brighter. Now, the shape of the shadow depends on the spin in general relativity and on the inclination angle. But suppose that you are looking at edge on. Well, in the case of a Schwarzschild, is a perfect circle, no matter which inclination. But in the case of a curved spacetime, and for rapidly rotating black holes, what you will see is that this part is not symmetrical to this part. In fact, this part is almost cut, and the whole center of the image moves to the right, assuming that the spin is rotating like so. So in principle, if you were able to just determine the edge between light and no light, and I'll explain it is not dark and it's just darker, then you can tell a lot about the spin of a black hole. Now, what we have observed, and maybe I'll go back to this, what we observed here, and this part of here, this is what we call a shadow, okay? Let me explain what is a shadow. Suppose that you have a black hole. That's the event horizon. And suppose that the black hole is somewhere in front of a source of radiation. So you may imagine that there's going to be this source of light emitting photons, rays of light. And then you are here, standing here, measuring the light. Well, what you can imagine is that there's going to be some light that hits the black hole. The black hole absorbs this light. This is the photons that are within the cross-section of the event horizon. And so if you are here, you're not going to see it. But there is more to that. In particular, there are photons that are not hitting the horizon, but are getting close enough. And close is within the unstable photon circular orbit. And also those photons will be trapped. They will just go around a few times and then be trapped. So at the end of the day, if you're over here, you're going to see a deficit of light because there are going to be some photons which either are going directly into the event horizon or eventually into the event horizon. At the end of the day, what you see is a darker region. We call this a shadow. Now, to give you sizes, the size of the event horizon is 2m for a non-rotating black hole. The photon circular orbit is at 3m. And the size, which is the projection, or if you want the impact parameter at the circular orbit, is square root of 27. So its square is roughly 5.5. So the size of the shadow is larger than the event horizon. And the dark region here is not the event horizon. You can't possibly see an event horizon. By definition, it's a null surface. You cannot see any light coming from it. Another thing that you can appreciate from this picture is that this region over here doesn't have to be black. It just has to be darker. And the reason is that if you imagine that there is some plasma here that is emitting light, this light would have no problem reaching the observer because there is nothing preventing it. So this region is the shadow, is the projection of this circular orbit, and is just simply darker than the rest. I hope this clarifies a bit the difference between event horizon and the shadow. Now, as a theorist, we don't know, well, we didn't know a lot of things, so we had to investigate a large space of parameters. In particular, we had to consider the mass and spin of the black hole if we were considering general relativity. We had to consider alternatives to black holes, and this could be other black holes in other theories or other objects which are maybe without a horizon or without a surface. Then we had to describe the possible dynamics of the plasma. Plasma dynamics depends very much on the magnetic field, and the type of accretion flows that you can produce is distinguished in sane or standard accretion, disk, or in MAD. And the difference between the two depends on the properties of the magnetic field that is advected through the flow. But anyway, let's say there are two classes of possible models that we needed to consider. And then there is a problem of the dynamics of light and its properties. In particular, we think that the light we observe is coming from synchrotron emission. But if you remember how synchrotron emission works, this is depending on the energy distribution of the electrons. And so according to what distribution you give to the energy of the electrons, you will have rather different images. And you may have images where the disk or the jet is dominating. And then last but not least, you have to take into account the fact that we don't know what is the orientation. So there are two free angles that need to be specified. So how you solve this very large space of parameters is just do simulations. We've done 50 high resolution simulations. About 50% of them were done here in Frankfurt. For each of these simulations, we build possible scenarios where we change the properties of the plasma and of the electron distribution energy. And so as a result, you build things like this, a very large library of possible images. So these are movies when you consider a situation where the shadow is very small, others where the shadow is very large, where things are moving in the clockwise or counterclockwise direction. There are all of these possibilities. And of course, all of these then change depending on the inclination of the observer. And in this way, we built 60,000 images. And of course, we have just 4 images we have observed. So you have to find out which of these 60,000 images, which are physically consistent and correct, but not necessarily true and representing reality. And for this, you need genetic algorithms or Markov chain Monte Carlo pipelines to find the best match. Let me explain to you a little bit how you do this. Each image, as I explained, can be decomposed into this visibility amplitude or closure phases. These are the real and imaginary part of the visibility, this quantity that I mentioned at the beginning in Fourier space. So you can imagine that given an image here, a synthetic image, you can have it represented with these green dots. And then you have some data, which is the one you have actually measured with the telescopes. And what you do is you just change your model every time there is this during a simulation, and then you find out which of these snapshots best fits the data. Okay, so you then build up a chi-squared classification, and then you can decide which of the images, of the synthetic images, best matches the data. Now, what I've shown you is in what is done in visibility space. If you want to do this in image space, you can think about the following experiment. Imagine that you are searching for a phase in a stadium full of people. Stadiums are normally, having 60, 70,000 people. So what you have is an image of someone, you don't know anything about this person, you just know he's a person. And then you just go and cross-check this image with all the ones of the people in the stadium. And you reject those that are obviously wrong, but then there are a few which are sufficiently close to the one you have. And the fact that you have so many is because the quality of your image is not very good. And then you have to accept the idea that you don't know for sure whether the person is in the stadium. There is just a certain probability that this person is in the stadium. And once you check the possible candidates, then you can convince whether or not this is the person you're looking for. But you nevertheless learn 2 things from this exercise. The first one is that all of the images, all of the persons that match have long hair. Okay, so you've learned that this person has long hair. And the second thing you learn is that they are all women. So you have singled out a very specific class of people in the stadium. And now you've learned that the person you are searching is most likely a woman and with long hair. And this is not the whole information. You don't know the identity, you don't know the color of the eyes, but you still know much more than before. So this is an example of this experiment of comparing observation study on the left with a theoretical model. And as you can see, sometimes we get a very good match. And because we know everything about this model, then you can think that you know everything about this model. Well, in principle. In practice, it's not as easy. And the reason is that this very good match can happen too often and for very physically different systems. So these are three images that match equally well the observations, and they refer to very different black holes. In particular, this is a counter-rotating black hole, rapidly counter-rotating. This is a rapidly co-rotating black hole, so positive or negative spins. And this is a Schwarzschild black hole. It's not rotating at all. So if all the information that you have is just the image, then there are degeneracies in your analysis. This is both good and bad. It's good because this gives you very high confidence. And what you've seen here is a black hole. Just remember the example I've given. You have very high confidence that the person you're looking is a woman with long hair. On the other hand, the bad thing is that you are blind to spin. You cannot distinguish spin. And so right now, that's the status of things. We need more accurate observation in order to distinguish these methods. Effectively, there are many other ways in which you can appreciate which of these is right. For instance, you can exclude this one if you start now putting in additional information, like for instance, how much power is in the jet and so on. But if you look and stick just to the image, that's all you can say. So, Mariusz, how much time do I still have?
Just go ahead, around 15 minutes. Yes, still is admissible. 10, okay. 15 minutes. So what I've shown you and all we have observed is consistent with a Kerr black hole in general relativity. And general relativity is the simplest, most elegant, most natural, best tested theory of gravity that we have. However, this is an observational science. You observe things, you cannot experiment. You can only obtain information through light or waves. And so the generative explanations are possible. I've just given you a very simple example of different models with different spins giving you exactly the same match to the data. So, if you want to start testing theory of gravity, this is not at all trivial because of these degeneracies. Besides, it's not trivial because you have hundreds of possible theories that are available, and sorting out which one matches and which one doesn't is not at all easy. You can use an agnostic approach and agnostic approach, and you can use either or both of them to exclude or allow for alternatives. Let me explain what I mean by that. In the agnostic approach, you can rely on the fact that you don't need to solve the field equations. This is because essentially all of what we're seeing comes from geodesic motion of particles onto a fixed background spacetime. So all we need is essentially a metric tensor in a given coordinate systems. And you can put here, the Kerr metric, the Schwarzschild metric, the Kerr-Newman metric, whatever metric you want, and then check with the observations. I find this frustrating because I don't want to always forget one metric that I should have considered. And so what I've come up with colleagues is a generic parameterization so that I go from a G mu nu that describes a black hole spacetime to a G mu nu that describes any generic black hole spacetime in terms of some additional coefficients. So this is a parameterization. And of course, because of the way I construct things,
general relativity is just a case where all the coefficients are zero. Now, this is an approach that many people have tried in the past with different levels of success. This approach, which is developed with Alexander Zhidenko and Roman Konoplia, is, in my view, the most promising one because it essentially is using two tricks. The first one is we're using a coordinate compactification. So instead of having a domain, the radial domain going between the horizon and infinity, we introduce a compactified coordinate. And so our domain, instead of going between 2 and infinity, in case of Schwarzschild, goes between 0 and 1. So it's much easier to impose boundary conditions at asymptotic infinity. The second trick is that any expansion you can come up with of this metric will be singular at the horizon. And the best way of handling singularities or poles is to use a Padé expansion. So what we've done is essentially we parameterize our metric function in terms of continued fractions of this type. So this is one way of splitting the metric function GRR. You write in terms of coefficients of this type. And then depending on which truncation you decide to work at, say you work at A3 equal to 0, then all of the other coefficients are automatically 0, and you are left just with the first two. So it's very easy to truncate the series. And if you do this, then you will be surprised to learn that with just a few parameters, maybe 2, 3, you can represent accurately, with a precision of a few percent or less, any known black hole space-time metric that people have played with. Okay, we have a paper where we have the expansion and the values of this coefficient for all the most known metrics. So this is a way in which you can do this type of exercise and do a measurement, and then out of the measurement get values of these coefficients. And then in this way, you don't marry any specific theory. You just say, I have measured a black hole as parameter A0 equal to something and B0 equal to something else. And then, of course, if A0 and B0 happen to be 0, then you know you're doing general relativity. And of course, that's exactly what we've done. The other approach is to consider alternative to curved black holes, to specify very specific ideas. And in this case, there isn't been a whole lot of progress, but we have done some progress. In particular, we have considered accretion onto a dilaton black hole and accretion onto a boson star. Let me explain what is a dilaton black hole. Well, dilaton black hole is a black hole that comes into a theory where you have additional fields associated with a black hole. In particular, there is one field, the dilaton field in spherical symmetry, which is a free parameters. And you can tune this free parameter to match the properties of a curved black hole, because you want to have a fair comparison. You want to compare, say, a curved black hole with a given spin, say 0.6, with a dilaton black hole, which has either the same horizon size or the same photon orbit or the same ISCO in a more circular orbit, in a more stable circular orbit. And as you can see, by just playing with the values of this dilaton parameter, you can match either. And of course, we tried all of them, but the ISCO is the most sensitive because it is where most of the emission comes from, around the ISCO. So here is an example, side by side, of a curved black hole accreting and a dilaton black hole. They have the same ISCO. They have different horizon sizes, as you can see from the movie. And you can look at these movies yourself for quite a long time, and then you can realize, well, obviously they are different. But of course, we're not going to see, fine details of magneto-aerodynamics. What we will see is images. And so what you can do is take the image you would obtain, say, in the case of Sagittarius A star, of Kerr and a dilaton black hole. And if you look at them, they are different, but they are also very similar. And if you, in addition, take into account the fact that you may have a scattering, then the differences become even harder to distinguish. And that is why the conclusion you can take, and this is the present conclusion, is that at the moment it's not possible to distinguish between the two black holes. And that is why the title of my talk is not the first image of a Kerr black hole, but it's the first image of a black hole. We still don't know whether this is a black hole in generativity or in another theory. Of course, generativity is our preferred explanation, but we cannot exclude any other at the moment. Maybe it's not a black hole at all. Maybe it's something else. Maybe it's an object which has a circular orbit, so produces a shadow, but doesn't have an horizon and doesn't even have a surface. Well, there are such objects. These are called boson stars. These are, in particular, the one we consider is a non-rotating boson star. You just take the Klein-Gordon equations for a complex scalar field. You choose a potential, a quadratic potential is the simplest you can come up with. And then you obtain an object whose compactness is rather large, okay? It's not as compact as a black hole, but when seen from a distance, it looks extremely compact. So then you can do exactly the same exercise, produce a torus unstable, and let it accrete onto a black hole, onto this boson star. And because the boson star doesn't have a surface, you can see that there is matter going very close to the inner parts of the center of the boson star. And this is because essentially, unless you are in this region, you are still able to lose angular momentum. Then once you reach very close to the origin, there's going to be a very strong centrifugal barrier that it will develop. And so at that point, you can no longer go in. Don't forget, you still have some initial angular momentum. And as you go in, you are not losing it. So you are spinning faster and faster. And at one point, you will just spin so fast that you will be ejected along the poles. You can do the same type of exercise. Well, let me go back maybe. No, I don't think I'm able to do that. Yeah, okay. What you can appreciate is that because matter can go right in the middle, right very close to the origin, the size of the shadow, you're going to be having light already from the very innermost regions. And so you would expect that if you see a shadow, or if it is not a shadow, a dark region, this would be much smaller. And this is shown over here. So here we're keeping the same mass. And as you can see, the size of the shadow is much smaller than the size of a Kerr black hole of the same mass. And then if you consider the fact that this would be observed with a radio telescope, you see that the size of the shadow is far smaller than the one you would obtain in the case of a black hole. Now, the size of the shadow depends on the mass. So you could say, well, I'm seeing an object which has the right size of the shadow is just much larger than you would otherwise assume. The point is, in the case of M87, so this logic is perfectly right. In the case of M87, doesn't work. If you want to fit the size of the boson star over to that of M87, you will need to have a mass which is twice as large as the mass we have measured, and is in great clash with any other astrophysical measurement of the mass of M87. And that is why, on the basis of this example, and at least for the boson star that we've looked at, which is, as I said, the simplest, it is possible to distinguish a boson star and an accreting black hole. So I want to close it up here so that we have maybe some time for questions. Black Hole Cam, this European project, which in many respects has been also the seed of all the EHT, has covered all of the aspects of these observations and has played a major role in this campaign. We have, in particular in Frankfurt, we have studied accretion onto Kerr black holes very extensively. We have done in a couple of years more progress, I think, than was done in the previous 10 years. And we've had to look at a large number of subtleties and physical subtleties that we had not appreciated before. Kerr black holes seem to be a perfect explanation, but as a theorist, we have to nurture the doubt. And so we've been looking at other black holes, alternatives to Kerr black holes, either in terms of boson stars that can be distinguished, or other black holes, which right now cannot be distinguished. I'm often asked, what is the most important contribution of the EHT? So, at face value, the most important contribution is having shown that in the center of galaxy, of supermassive galaxy, there are supermassive object that looks like supermassive black holes. Now, you may say that this is an obvious statement, and that's something you already have learned in your first course of astronomy. But when you've learned it, it was a conjecture, an hypothesis. Now this is the first time that it has been proven. So it's an important confirmation of a conjecture. But for me, as a relativist, the most important thing is the EHT observations have transformed the event horizon from a concept, from a null surface to a testable object. And anyone working in science appreciates that this is the most important step. Going from something which is testable, which is not testable, which can be subject to any possible interpretation, to something that can be tested is the first step in the scientific method. At this point, we can have many, many theories. We hope to have many, many theories, but at the end of the day, these theories have to be confronted with observations. And now we have these observations. So the most important contribution to me is having transformed a mathematical concept into a testable object. Thank you for your attention.
Thank you very much, Luciano, for this excellent talk. Really, you've shown a lot of nice simulations and a lot of data and a lot of theory behind that. I would like now to start the discussion. I also should address the people who are watching us on YouTube. You may also put the questions on YouTube, and we will transfer them into Zoom and ask the lecturer. So I can see 2 questions on chat, and then there is one question by the raised hand, as far as I could see. So first question is from Krzysztof Domański. He would like to ask if it would be possible in the near future to put a bunch of telescopes in an orbit around the sun and increase the resolution.
Yes, that's a very good question. And the answer is yes. Because this technique relies on having the planet, and a planet, as a given size, and you cannot make it bigger. If you want to have a larger baseline, you have to have either a telescope on Earth and one on a satellite, or a bunch of them on satellites. Actually, this is not very expensive to do, because you can have telescopes which are just a meter or a meter and a half in diameter, and you don't need to push them to very large distances from the Earth. You can do them on rather close orbits. And so we have worked out in our papers that have explored this, that if you have 3 of such satellites and you put them at a position of about 15,000 kilometers from the Earth, then you can have a constellation that will observe and cover this visibility space over 6 months only. We will have a factor 10 more accuracy. And then all of a sudden, all of these blurry images will become very highly and sharp, and we can start making, addressing very important and detailed questions about different theories of gravity. At that point, it'll be possible to distinguish black holes of different nature. We can test a lot of details of the plasma physics. So again, it's a very good idea. We are working on this, and we hope that maybe in the next 20, 30 years, the space agency will find our proposal interesting.
Okay, we have 3 questions from IK. The first one: are the published images of black holes just the best match from the numerically generated library of 60,000, or the latter are used just to filter out noise by directing the algorithm? That's the first question out of 3.
So let me answer. We treat as 2 distinct sets, theory and observations. And theory is, just into a servile role. Observations are what matters. Observations are the reality. And theory has to explain them, and the theory has to match them. It's not the other way around. So if there is noise in the observational images, we have to reproduce that noise, understand why there is noise, and reproduce it. And that noise is the result of some physical process. But it's very important that you appreciate it's observations that are the important reference here.
Okay, the next one is, what is the distance, in inverted commas, between different numerical images in the library in terms of the parameters of black holes, their orientation, etc.?
Well, that depends on you know, what is your parameter, because it's a multidimensional space. I think there are 16 dimensions in this space. So depending on which dimension you're going in, you can find that maybe it's you will have two images which are very similar because the maybe the emission, the energy of the emitting particles is very similar, although the properties of the black holes are very different. So there isn't a simple answer to this question. It depends on which parameter you are looking at. But if you fix everything, okay, everything is fixed. So spin, mass, orientation, energy of the electrons, and so on, then images will be similar also because they are coming from very similar states in the plasma. So if you want to see a difference, you have to sample the plasma at a sufficiently large time or sufficiently later time so that, you know, the memory of this plasma configuration is erased and you have a completely different new configuration. Think about water falling out of a waterfall, okay? At any time, there's going to be a different amount of water and different level of water and distribution of water. But if you are comparing very close times, then they will look similar. So you have to really look at a sufficiently large distances in time.
Thank you. And the third one is, which numerical algorithm of simulation of MHD on black hole backgrounds is currently the most effective in terms of speed, precision, and robustness?
So because we had to do a lot of simulations, we haven't been very sophisticated. So we used rather simple second order finite volume shock capturing methods. These are not the best that the numerical analysis offers, but they are very robust and very simple to use. And that's what we've been using. So finite volume, second order with adaptive mesh refinement.
Okay, the next one is, you mentioned that the analysis in the image domain is not good at distinguishing black holes with different spins or other parameters. Would the situation be better in the Fourier UV domain?
No, unfortunately, you know, it doesn't. It doesn't depend on whether you do it in the Fourier domain or if you do it in the image space. It's just a degeneracy. And to explain this, maybe let's see if I have a. Yeah, I don't know. I'm always a bit confused about how to do this. Let me see if I can explain this. No, I don't think I have the slide with me. Well, yes, I actually have it. Oh, no. I need to skip it. Okay, so these are 4 images coming from very different simulations with different prescription of the energy of the electrons. And you know, they look, if you convolve them, they will look very similar. And you can ask yourself, okay, but in this image, where is light coming from? And this is where our intuition plays tricks on us, because we normally tend to think that if there is light in an image, it's because it is coming from matter that is the closest to us. But in this picture, there are three different contributions. One coming from the disk. There is a jet coming towards us that you don't quite see, but is there. And then there is a jet that is coming, that is moving away from us. And is also contributing, but is also emitting light. And so depending on what is the distribution of electrons and where you put these electrons, where you put them mostly in the disk or mostly in the jet, you can get very different contributions. And this is shown here. So in this image, I am splitting the image on the left in three parts. One which is the midplane, so the disk, the other one which is coming from the jet close to us, and the other one is coming from the jet away from us. So the first image is mostly the disk, bit coming from the jet, very little coming from the receding jet. In the last image, which, as I said, would give you a very similar result, there is very little light coming from the disk. There is a bit of light coming from the forward jet, but most of the light comes from the backward jet. So this is to say that it's very difficult to know where the light comes from, and therefore it's very difficult to remove these degeneracies. The only way on how to do this is having longer, repeated observations at higher resolutions, so you can distinguish what is stochastic from what is instead stationary. And this will allow you to distinguish different models, for instance. Other ways in which you can do this is by looking at the distribution of magnetic field, the intensity of the jet, and so on. And then once you put all of this into the game, then you can say, okay, now this model over here, sane, high 10, this is really not possible. And rather, I think it's either this one or this one here. So there are ways in which you can remove some of these degeneracies.
Okay, thank you very much. We have a series of more. I would like to ask whether it will be possible to exhaust all possible alternatives to GR, assuming we exactly measured the shadow size with perfect precision. It's from Misbah Afrin.
Well, you know, generativity is a deterministic theory. So it has a single prediction, a single solution, a unique solution to a given set of initial data. So if you know, not only have a perfect observations, but you also know perfectly what are the physical conditions, then perfect observations and perfect knowledge of the physical condition will give you a unique solution to your problem, and therefore will allow you to select the unique theory that produces this. However, you know, let alone the fact that we will never have perfect images, we will never know exactly what are the physical conditions near a black hole. And so I'm afraid you will always have to live with the idea that, just like in the image I've shown you, that you're going to have a certain confidence that what you're seeing matches a given theoretical prediction. And you are confident that, you know, this is the best possible explanation. And but I'm afraid you will always have other alternatives, maybe because they are built on purpose to match exactly what you're seeing, that will you know, provide an equally good match to the observation. At that point, you are just left with yourself and, you know, maybe with Occam razors. You try to obtain try to defend the explanation which is the simplest and most natural, rather than the most sophisticated and unnatural.
Thank you. From Fabian Wagner, is it possible to project when we will be able to be quite sure whether we are actually witnessing a Kerr black hole or not, i.e. when most of the alternative models will most probably be ruled out?
No, I think it's very difficult. You know, as I said, it depends on what is your your fate, your amount of fate. If you are a skeptic, you will never be happy. If you are, if you are already convinced, you can already say, yeah, this is a Kerr black hole. I don't need anything else. No matter what theory you will give me, I think this is GR.
Okay, the next one is, can you see any time evolution in the image?
What we do, we see the image changing from day to day, but then when you try and find whether there is a correlation, if you remember, let me go no, for some reason. If you remember the 4 images, here, they are different, okay? So this is telling you that there is some evolution between April 5th and 6th and April 5th and April 11th. So then you can ask, okay, can I model the difference in the appearance? Is there any correlation? Can I say that there is, a brighter spot here and this is just becoming another spot over here and so on? Then you find out that it's not so easy, okay? There isn't any clear correlation between these images. Now, that's because M87 has 6.5 billion solar masses. And now the time scale, just take the time scale of orbit around the ISCO, is of few tens of hours. In the case of Sagittarius A star, which is another object we've observed and we will publish soon, then the correlation is far closer, and the evolution is far closer. You can see really images flickering on the time scale of minutes. And this is both good and bad. It's good because it allows you to maybe track and possibly track the motion of matter very close to the black hole. It's bad because you have a lot of variability. And so it's like this variability prevents you sometimes from seeing even the image, because the image is shadowed. Sorry, the shadow is shadowed. The shadow is erased by the fact that you have maybe a flare that is producing so much light that covers the shadow. So you have to find different techniques, far more sophisticated than if you have M87 to see the changes in the images or the non-changes in the images.
Thank you. The next one, regarding the image comparison method you have shown, I'm curious about the computational effort that has been required to obtain such a big library and then doing the image comparison. Could you comment on that? So,
as it happens, the image comparison is not very expensive. That's because the technique we use are very simple and robust, like chi-squared comparison. So once you agree about what is a fair way of comparing data with observations, then the actual comparison is maybe 10% of the time needed to actually build the synthetic images. So, once you build the images, then the comparison is just a piece of cake.
Okay, thank you. You mentioned that the agnostic approach considers conventional GA with additional parameterization and it does produce predictable results. Considering insufficient observation to distinguish the spin of a black hole, could this imply that the observations do not exclude the possibility of non-local interpretation of GA in the context of black hole characteristics?
Yeah, I'm not sure I understand the question fully. So in the case of an agnostic approach, essentially this uncertainty is reflected in the fact that the ranges in which these parameters can vary are very large. Okay, so you don't have a single number for every coefficient. You have that, given a certain set of coefficients, they are valid within a certain range. And the hope is that as the observation become better and better, the ranges in which these coefficients are varying become smaller and smaller. And maybe they become so small that you are happy to consider them to be equal to 0. It's not very different from what is the speed of propagation of gravitational waves. Right now, you don't know that it's exactly the speed of light. You just know that it is differing from the speed of light by 10 to the minus 15. And you can think this is enough for me to say that gravitational waves move at the speed of light or not. Whether you can see non-locality, well, again, I need to know exactly what you mean with non-locality, whether you have a specific metric in mind, but any metric you have in mind, I can characterize in terms of coefficients. So I can check whether or not the values of these coefficients are compatible with that theory. And right now, the uncertainty is so large that I'm pretty sure that any non-local black hole would be compatible.
Thank you very much. I don't see maybe raised hands, but if there are some, I can ask you in a moment. I have a question. How about this boson star, which is considered as kind of a alternative of the black hole? How strongly relativistic is it? For example, putting this in terms of the lensing effect or multiple images.
So you know, there is in the case we have considered, this is a pretty extreme case. Let me go back to where is it? Okay, so you know, how do you express the relativity or the strength of the gravitational field of a boson star? Well, you know, one way of doing this is using the compactness. So the ratio between the mass and the radius, and of course, you know, the radius is infinite in a boson star, but you can say that you take the radius where 99% of the mass is present. So because these objects are extremely condensed object, they are infinitely extended, but they are very, very condensed near the center. So in this case, you know, the compactness of this object is 6%. This is not any close to you know, a black hole. Black hole is 0.5. A neutron star is even more compact, but put on the scales of a supermassive black hole, this is a very compact. So compact that you can see a shadow, okay? So the shadow I showed you before, this object does have a shadow. This is a boson star that has a shadow. So it has an unstable photon orbit and so can produce a shadow.
Okay, thank you very much. I have one more question from Igor Kanatchikov. Can we expect images of black hole binaries soon?
Well, you see, first of all, I don't know which masses you're thinking about. If you're thinking about stellar mass black holes, ones that are seen in gravitational waves, the answer is no, definitely not. They are way too small to be seen. If you're thinking about supermassive black holes, then we have to ask, you know, whether they are sufficiently close to us that we can actually see them with a given resolution. So right now, you also have to bear in mind that right now we don't have any evidence of the existence of supermassive black hole binaries, okay? We know there are binaries in stellar mass black holes, but when you go to supermassive black holes, there isn't any firm evidence. There are some tentative suggestions. One of them is OJ 87, where you see a black hole and another black hole that maybe is going around it every few years. But there isn't, you know, there are possible alternative explanations. So right now we don't see any binary black hole, supermassive binary black hole. If maybe in the future we will see them, and if it happens that they are sufficiently large size and they are sufficiently close to us, then we can use exactly the same technique and image also those binaries.
Okay, thank you very much. I think you answered. Okay, there is one more. Have you tried to compare contribution of different components, disk, jet, etc., with what is concluded from X-ray observations to see how consistent they are?
Yes, so we have done this. The conclusion that I was mentioning, we can't tell about a spin, is if you just look at the image. But if you start putting in all the other information that we have, in particular from X-ray observation tell us how much does light in the X-ray does M87 emit, how much power does the jet emit. And if you put in these additional conditions, then you can remove a substantial fraction of the possible models. In particular, because we see a very powerful jet, and we know that you need a sufficiently high spin to produce those jets, then all of a sudden, all very slowly spinning black holes are excluded. Similarly, some accretion models where you have weak magnetic fields are also excluded. So at the end of the day, if you combine all of this information, you can screen quite a large part of the models. And yes, we do. In fact, it's not just X-ray that are important. We try to get all the possible information. Supermassive black holes emit at all wavelengths. So they have very broad spectra from infrared over to gammas. And we try to model all of these different pieces so that we can learn a bit more about the properties of the black hole. There is a paper that has just been produced in my group and will be published in the next couple of weeks in Nature, where we show that if you use a rapidly rotating spin black hole pointing away from us and a mad type of accretion, then you are able not only to match well the morphology of the jet, but you're also able to reproduce accurately the spectrum, the energy spectrum at all the different wavelengths from X-ray to radio.
Okay, thank you very much. One more. In your opinion, can we say that we have already seen the photon ring? I remember that some people argued that so far we only saw n equals to 0 light rays. N is the winding number.
Well, once again, I think it depends on what is your level of skepticism. If your level of skepticism is very high, then you will not be happy with any of these images unless you see an high-end image. I don't think we've seen firm evidence of the presence of a light ring. We do have evidence, though, that what we see is consistent with the existence of a light ring. So I would put the conclusion the other way around. Given what we observed, this is perfectly consistent with the existence of a light ring, but doesn't prove it, unfortunately, and we need a higher resolution. So that's my view.
I think that we can't count these photons orbiting many times at the moment. This is what I understand, yes. Okay, Luciano, I would like then to thank you very much for this excellent lecture and all the participants of this lecture for very interesting questions. I would like to remind all the people who listen to us that this was the lecture by Professor Luciano Rezzolla, the first image of a black hole, and the lecture was organized as a parallel event to the conference Alternative Gravities and Fundamental Cosmology, Alte Cosmofan 21, organized by the Szczecin Cosmology Group at the University of Szczecin. Thank you very much to everybody and have a good night.